Swayam Prabha. Digital India. Educated India.
So, students, this lecture is devoted to fitting of distribution. In the last lecture, we have talked about what is the meaning of a probability density function and distribution function, and we have also given you examples of a number of probability density functions, discrete, continuous, like binomial, Poisson, normal, etc. In this lecture, the focus is on how to fit a distribution, and the next issue in this lecture would be that once a distribution has been fitted, how do you test whether you have fitted a right distribution or not. So, I start. The first thing is to define what is fitting of a distribution or model. Identifying things like which theoretical distribution model describes the data best. Second, what are the values of the unknown constants of the distribution. These two things are most important in fitting a distribution. First, identifying whether say a negative exponential, binomial or Poisson or normal, and there are hundreds of distributions actually. The practitioners know that in this kind of situation that kind of distribution should be used. So, first you identify which distribution to use, and then second to you remember I told that each distribution is a family of distribution. A specific membership of the family of distribution depends on the values of the unknown constants or parameters. So, after deciding which distribution to fit, such as normal distribution to fit, we need to estimate values of mu and sigma. This is the meaning of estimating the parameters of the distribution. So, these two things are basically part of fitting of a distribution. All distributions contain a variable and a number of unknown constant, they are parameters, and I am referring to estimation of them. Distributions may have one parameter, Poisson distribution has only one parameter lambda, normal distribution has two parameters mu and sigma, there are distributions which have three parameters. So, that depends, and distributions may be deterministic or probabilistic, but in case of fitting of a probability distribution we are referring to probabilistic situation only, we are not dealing with deterministic distribution. And after fit means as I said that once you have fitted the distribution, you may replace original data by the theoretical distribution for analytical and predictive purposes, but for doing this you have to check the goodness of fit of the model or the extent to which your chosen model fits the empirical data, because if the chosen model does not actually fit the empirical data, then your efforts are wasted. You cannot use theoretical model for analytical and predictive purposes. Now, why fit a theoretical distribution? Curiosity among quantitative sociologists to explore a mathematical statistical law of human behavior. For example, in case of deterministic processes, in sociology we have gravity model of migration, and in probabilistic models we have Markov process of migration. This Markov model is also used for studying social mobility from one occupational class to another. Now, raw data often contain errors. For example, data on age in completed years suffers from the problem of age heaping, and we need modeling to smooth out the distribution, empirical distribution, and to have a better assessment of the pattern or the nature of distribution of numbers according to age. Once developed, the models can be of help in explaining behavior, distance and migration. For example, in case of gravity model, you can explain why number of migrants to distant places is less, why number of migrants to nearby places is more, and the model can also be used for predictions. For example, sensor data on age may not be reliable, it suffers from fluctuations, and those fluctuations are due to age heaping, and you may like to fit a stable population model to data on numbers against age. What is stable population means is that under certain conditions, numbers at age x at time t may be expressed as C x t equal to b, a constant, multiplied by exponential minus r x multiplied by p x, where b is the birth rate, r is the growth rate of population, and p x is the chance of survival till age x. Here is a comparison of actual and stable equivalent age distributions. This is actual, it suffers from fluctuations, and this is stable, a freehand smooth curve kind of curve. Now, some of the fluctuations sometime in actual data like this may be real, they may emanate from fluctuations in births and deaths over time. But I was referring to problem of age heaping which distorts age distribution, and stable population model can be used for removing distortions produced by age heaping. If these fluctuations are real, then of course, stable population model would not work. Then we have to look for causes behind fluctuations, rising and falling of population periodically, cyclically. It may be due to baby boom, it may be due to sudden rise in life expectancy, or it may be due to migration. So, then we have to first discover what are there assignable causes in the fluctuations in population numbers. Statistical applications are not routine, and you have to make full use of review of literature, your experience, your judgment in deciding whether the fluctuations are due to real reasons or they are due to distortions in the data due to response bias or age heaping or factors of that kind. In empirical works, in the last lecture, we saw that we begin with empirical data or hard facts, prepare a frequency distribution, identify what mathematical expression will generate this kind of distribution, estimate parameters from the data, estimate expected frequencies under the theoretical frequencies, and finally, for goodness of fit, you test whether the assumed distribution is okay by comparing the observed and expected frequencies using some method like chi-square or Kolmogorov-Smirnov test. We will talk about these things in a minute. Now, theoretical distributions are identified with a number of things, a number of considerations such as range of the variable, whether the distribution is discrete or continuous, graphical picture of the distribution or shape. Different distributions have different shapes. A normal distribution has a very different shape from say negative exponential distribution. Negative exponential distribution starts from a peak, from mode, and then the value is constantly decline. But in normal distribution, values start from minus infinity and probabilities or frequencies rise as the value of the variable increases, reach a peak and then start declining. Algebraic function or a probability density function is chosen for the given distribution. Then there are parameters or unknown constants, they are estimated, and you look for what does literature suggest regarding their domains of applications. So, what is in fashion? In literature, suppose everybody is using normal distribution, you also use normal distribution, then it is safe. And for PhD students, it is always safer to go according to fashion. If everybody is using normal distribution in a given situation and the researcher uses something else, that is okay, but then in that case you have to justify that while for a given type of data most people are using normal distribution, you are differing from them and you are using some other distribution. Again example of deterministic distribution, gravity model of migration is deterministic. We show that Mij is k into Pi into Pj divided by Dij. Pi and Pj are populations of places I and j, Dij is the distance separating the two. Now, for fitting purposes, means for estimating values of k, you can use log m equal to log k plus log Pi plus log Pj minus log Dij. A stable model is also a deterministic model, by the way, although it includes the concept of probability Px, but it is also a deterministic model. Cxt equal to b exponential minus Rx into Px, or log of Cxt equal to log b minus Rx plus log Px. Now, let us see what are the probabilities or frequencies at different values of the random variable. Let us first take the case of a simple distribution like Poisson distribution. The mathematical or algebraic expression of Poisson distribution is given by f(x) equal to e raised to power minus lambda, lambda raised to power x divided by factorial x, and the values of x go from 0 to infinity. Now, these are the values of x 0, 1, 2, 3, 4 up to infinity, and the values of f(x) are e raised to power minus lambda, e raised to power minus lambda into lambda, e raised to power minus lambda into lambda square by 2, and the mean and variance of this distribution are lambda. If you have a discrete distribution with same mean and variance, it may be a Poisson distribution. For lambda equal to 2, you have a Poisson distribution like this, lambda is replaced by 2, and probabilities of occurrence of 0, 1, 2, 3, 4 etc. can be computed. You do not have to go up to infinity. You see, as the values of x increase for lambda equal to 2, the values of probability also increase 0.1353 to 0.2707, then for 2 also it is the same value, for 3 there is a fall, and then for 4, 5, 6 values of probability start falling, and maybe you have to go only up to 6 or 7, x equal to 6 or 7. Beyond that, the probabilities of having values 8, 9, 10 etc. are almost 0. Mean and variance of this distribution is same, it is 2. A typical case of Poisson distribution, let me assume that there is a distribution, observed frequency distribution, number of crimes in a year in a sample of 10,000 villages. A sociologist makes a survey of 10,000 villages and tries to find out the frequency distribution of number of crimes. Now, number of crimes may be 0, 1, 2, 3, 4, 5 and above, and the values are 1353, 2707, 2707, 1805 and so on. Looking at the nature of data, that values as the value of x rise, values of probabilities initially rise and then fall, and it is a discrete variable. Maybe one can also calculate mean and variance are found to be close to 2. Then the researcher decides that Poisson distribution will fit these data, and we have just seen that for a Poisson distribution with lambda equal to 2, probabilities are 1353, 2707, 2707 etc. And sum of all the probabilities will be 1, sum of all relative frequencies will also be 1. You can calculate 1353 divided by 10,000, 2707 divided by 10,000 etc. and add, you will again get 1. There are very small differences between observed frequencies and frequencies obtained by using a Poisson distribution. Like here you have 1353, maybe your relative frequency in a Poisson distribution is 1353, but observed frequency may be slightly different. Imagine that it is 1357 and not 1353. Maybe if it is more, then some other frequency will be less, because total has to be 10,000. Now, we have to decide whether this difference of 1353 and 1357 can be tolerated. Can it be due to sampling fluctuation? Suppose here in place of 2707 you have 2710, can it be tolerated, or you have 2610, or you have 2500, or you have 2903. So, can these differences between observed frequencies and estimated frequencies be tolerated? These are relative frequencies which are obtained by dividing these numbers by this 10,000. Fitting of a Poisson distribution means preparing a frequency table, calculating mean and variance. Are they same? If they are slightly different, maybe choose the mean, take it as lambda, fit a Poisson distribution, find out theoretical frequencies for the Poisson distribution, convert the above into expected frequencies, multiplying them by sample size, and compare the observed and expected frequencies. How? You will have as many differences between observed and expected frequencies as the number of values of the random variable. You would like to have a unitary value for difference between observed and theoretical frequencies. Again, as we calculate variance or sigma square, using the similar logic, you can square the differences. Some differences are positive, some are negative. If you simply add them up, you get 0, and divide the squares by expected frequencies. In variance, we add all the squares and divide by n, but in this test which we are discussing to check whether observed and expected frequencies are same, we divide the squares of differences between observed and expected frequency by expected frequency, and then we add. This is called chi-square, and this gives you the calculated value of chi-square. If it is small, you can say that the distribution fits, otherwise the distribution does not fit. Now, what is the meaning of small? For this purpose, we compare calculated values of chi square with the tabulated values of chi square with degrees of freedom, number of observations minus 1, number of values which you are comparing, number of differences that you are comparing minus 1, that is called degrees of freedom. And if you look for tabulated values of chi square, you will find that there are so many tables for chi square, and for each table there is a fixed degrees of freedom. For a definite degree of freedom, a definite chi square table has been made. So, look for how many differences you are comparing and take sum of squares of differences divided by expected frequency, that is called chi square. If your calculated value of chi square is less than the tabulated value is a sort of threshold. If you get a value, empirical value more than the tabulated value, then you say that our distribution, theoretical distribution does not fit the empirical data. And if the tabulated value is more than the calculated value, then you say that despite some differences between expected and observed frequencies, the model fits the data very well. And this you have to make this kind of table for calculating chi square, like values of the variable are 0, 1, 2, 3, 4, 5 plus observed frequencies are 1, 3, 5, 6, 2, 7, 0, 2, 2, 6, 0, 0. Theoretical frequencies which you get from the model are 1, 3, 5, 3, 2, 7, 0, 7, 2, 7, 0, 7, 1, 8, 0, 5. So, there are small differences between observed and expected frequencies. Find out the difference. There is a difference of 3 here, 56 minus 53 equal to 3. There is a difference of 5 here, a difference of 107. Some differences are more, some differences are less. Square the differences, 3 square is 9, 5 square is 25, 107 square is 11449. Then divide these difference squares by expected frequency, theoretical frequencies for lambda equal to 2, 1353. 9 divided by 1353, you get 0.00665. 5 square is 25, 25 divided by 2707 is 0.009. You add all these values, this is chi square. So, chi square calculated from the data is 9.38. Now, you look for how many values are there. You have 1, 2, 3, 4, 5, 6. You are comparing 6 differences. So, degrees of freedom will be 6 minus 1 or 5, and look for what is the tabulated value of chi square for 5 degrees of freedom. Your calculated value is 9.38, tabulated value for degrees of freedom 5 at 5% level of significance is 11.07. Now, since 9.38 is less than 11.07, you can say that the Poisson distribution fits the given data very well. And now, once you have fitted a theoretical distribution, you can forget about empirical distribution now, and you can use theoretical distribution to make any prediction. You can say that for analytical and for predictive purposes, or for predicting what are possibilities of the random variable, you can simply use Poisson distribution with parameter 2, and you can forget the empirical distribution. Empirical distributions will always have some errors which are smoothed out by using theoretical distribution. Now, can we fit a binomial distribution? Theoretically, yes, with 10,000 into p equal to p equal to 2 or p equal to 0.0002. theoretical probability would be C n x, n is the sample size. The probability, we are calculating probability of getting a value x out of n cases. P x probability of probability of x occurrences, and 1 minus p probability of failure, and this is 10,000 minus, means x time success or x time occurrence of the event, x crimes, and 10,000 minus x, this is the probability of non occurrence. Then x equal to 0, 1, 2, 3, 4, 5 equal to this. Now, practically calculations for binomial distribution will be very tedious, and you can also see that here whether variance is less than mean or more than mean, and accordingly decide. Normally binomial distribution will be used when the sample size is small, but when sample size is large, then you use Poisson distribution, provided the probability is low and sample size multiplied by probability is a small finite quantity. The same logic applies to all distributions. The logic of fitting a theoretical distribution is same for all distributions. Calculate mean and variance of the data, then write theoretical values of mean and variance. Theoretical values are the values of the distribution algebraic in terms of unknown constants, like in a normal distribution calculate mean and variance of empirical data, and mean and variance of a normal distribution are mu and sigma square. Equate the two. This equating the two empirical values of mean and variance and the theoretical values, this gives you estimates of mu and sigma square, and the method in which we compare mean, variance, or maybe other moments of empirical data with that of theoretical data, this is called method of moments. There are many other methods also for estimating parameters, but method of moments is most commonly used. With distribution 3 or more parameters, or in advanced statistics there are more advanced methods. There is a method of least square, there is a method of likelihood estimates, but this is a simple method. Since our purpose is only to demonstrate to sociologists how and where to make use of statistical methods. So, it is sufficient here to say that by equating mean, variance, etc. of empirical distribution with unknown constants of the model, mean and variance of the model, you can estimate their values. Now, this is a normal distribution. Remember that only those distributions which satisfy this equation are normal. Many students think that all symmetrical distributions are normal. No, all symmetrical distributions are not normal. Many symmetrical distributions may be more quartic or less quartic than a normal distribution. Only those distributions which are given exactly by this formula, they are normal. In theory, x can take values from minus infinity to plus infinity. In practice, it can be applied to variables in a narrow range also, because 95% values lie between minus 1.96 and plus 1.96 in standard normal variate, and between minus 1.96 sigma and plus 1.96 sigma when sigma differs from 1. We will need mean and standard deviation. For fitting a normal distribution, we will need mean and standard deviation of empirical data. It is a 2 parameter family of distributions, and there are specific tests to check normality of data. Researchers are often worried about whether the normal distribution fits the data or not. The methods can be probability plot, Gary's test, chi-square, Kolmogorov-Smirnov test. Probability plot is a graph between observed values of the variable on x axis and the z values of the normal distribution on y axis. Z is x minus mu by sigma. They are obtained from the cumulative frequency distribution of sample or empirical data, and since z equal to x by sigma minus mu by sigma, there is a linear relationship between z and x. So, if your graph gives a linear relationship, you can be sure that the distribution is normal. Also at z equal to 0, the x value shows the mean of the distribution. From this graph, you can also find out what is the mean and what is the standard deviation of the distribution. Mean is found at z equal to 0 and sigma is determined by the slope of the distribution. This is probability plot. These are observed values and these are z values corresponding to distribution, and mean is at 0 and the slope is sigma. This is the mean of the distribution and this is the slope. Gary's test is defined as mean absolute deviation from mean divided by standard deviation. Now, since mean absolute deviation from mean is a positive number and standard deviation is also defined in a way that it is always positive. So, G is always positive. For a normal distribution, G is expected to be 0.80. A normal distribution produces a G value of 0.80. Skewed and leptokurtic distributions have G less than 0.80 and platykurtic distributions have G more than 0.80. So, if you apply Gary's test for checking whether your distribution is normal or not, just calculate mean absolute deviation from mean, means differences between x values and mean, forget about their plus and minus sign, add them up all and divide by standard deviation, and then by sample size, because sum of absolute differences between variable values and mean divided by n is the mean absolute deviation from mean, and G is defined as mean absolute deviation from mean divided by ST. If this is 0.80 or close to 0.80, then you can be certain that you are dealing with normal distribution. If it is less than 0.80, then it is a leptokurtic distribution, more flat type, it is not normal, and if G is greater than 0.80, suppose G is 0.90, then you can say that the empirical distribution is platykurtic, more flat type. Leptokurtic is more peaked than the normal distribution and platykurtic is flat type. So, this is how you can judge whether your distribution can be normal or not. For G equal to 0.80, this is the distribution and this is normal. When G is less than 0.80, this green color curve, G is less than 0.80, then you say that the distribution is not normal, it is more peaked than a normal distribution. And more peaked means the value of the ordinate at mean is much higher than in case of the normal distribution. If it is blue type, this will happen when Gary's test G is more than 0.80. In general, fitness of distribution may also be examined, normal distribution or any other distribution, by using Kolmogorov-Smirnov goodness of fit test It is computed from cumulative frequency distribution of the model and the cumulative proportion for the sample data. So, one is model, capital F for model, S for sample data or empirical data. For all values of I, means for all values of x, you calculate capital F x and capital S x. Capital F x is distribution function for the model, capital S x shows the cumulative frequency distribution of the data in a relative sense, means cumulative frequency divided by population size or sample size. K minus S test is based on or Kolmogorov-Smirnov test, K for Kolmogorov, S for Smirnov. Ks test is based on the maximum absolute difference between the above two cumulative proportions, means capital F x and capital S x. Actually, if your empirical distribution is normal, then the values of f x and S x are same or similar. But if there is a difference between the two, that shows that the pattern of empirical data is not same as that of normal, and at any point the highest difference between S x and f x, theoretical and empirical, is m, and this as you compare tabulated chi-square and calculated chi-square, you also do the same thing with Kolmogorov-Smirnov test. So, you have empirical value, this is the empirical value of m. These are two cumulative distributions, one is empirical, another is theoretical, and the maximum difference between the two is at this point. This is the maximum difference, where is not important, but the maximum difference is this, and we compare this maximum difference with the tabulated value of Ks, and if this maximum is lower than the tabulated value, then we say that the distribution fits the empirical data, otherwise the distribution does not fit the empirical data. In this way, we can check whether normal distribution fits or not. Actually, we can also check whether any other distribution fits or not. We have to calculate theoretical frequencies, then cumulative distribution, and then relative cumulative distribution. And note that m is this absolute, means plus minus is not important. S may be more than capital F or capital F may be more than capital S. So, the difference may be positive or negative. We do not go into that positive negative part, we only look at the absolute difference without considering plus minus sign. Sometimes the maximum difference does not lie at any exact empirical point, means exact value of x, but between two values of x. In that case, m dash is computed as absolute difference between S x I minus 1, S for x I minus 1 means previous figure of x, and capital F is f x I. So, we compare S for a preceding value of x with a given value of x for f. Did you notice the difference between m and m dash? Yeah, this is the difference. The difference is that in this case, if you have x I here, then you have m, and if you have x I minus 1 as in this formula, then you have m dash. So, in case the maximum difference is not found at any exact point of x, then we go for m dash, and the logic is same, that we will compare m dash, calculated value of m dash with tabulated value of m dash, and if calculated value is less than the tabulated value, it means the model fits, differences are small, and if calculated value of m dash is more than the tabulated value, then the differences are too big to say that a theoretical distribution fits the data. In a way you are testing a null hypothesis, though more of this testing of null hypothesis we will see in another lecture, but I can say here that you are testing an assumption. Hypothesis is an assumption. What is the assumption? That for all values of x, for all values of the random variable x, the cumulative relative frequencies as obtained from the data are same as cumulative distribution function for the model. In other words, the null hypothesis is that cumulative frequency distribution of the model distribution and cumulative proportion for the sample or census depending on what kind of data you are checking are identical. Alternative hypothesis would be that no, they are not same, S and F are not same, and the alternative hypothesis then can be that S is greater than F or S is less than F. Not equal to is one kind of alternative hypothesis, and S is greater than F or less than F, this is another kind of alternative hypothesis. If we reject the null hypothesis that S and F are same, then we choose either this or one of them. This kind of alternative hypothesis is called two-side test, means S can be less than F or S can be more than F, and one specific hypothesis from here that S is greater than F or S is less than F, this is called one-side test. This is an example of fitting a normal distribution through Ks goodness of fit test. The values of x are 21, 32, 40, 86. The z values corresponding to these values of the random variable are these, which are obtained by calculating mean and variance of these empirical values and selecting a specific member of the family of normal distribution. Then we take capital F values and capital S values, compare the two, the maximum difference is here 0.0569, and if you take the difference between x I minus 1 and f x I, which is called m dash, this is m, difference between this and this is m, this is m dash. So, depending on your requirement you can choose m or m dash. Critical values of m have been tabulated, as I said, for different values of n or sample size. Sample size plays a very important role in selecting threshold values from the table with which calculated values are compared. Obviously, you can tolerate a bigger difference when sample size is small. There will be more sampling fluctuations. When I was talking about sample mean, I was telling that sample mean shows a normal distribution with mean of the population as mean and variance as sigma square by n. Same logic or similar findings are obtained for other distributions also, and actually in general we say that by using law of large number or central limit theorem that x bar always follows a normal distribution with mean as mean of the population and variance as sigma square by n, where sigma square is the variance of the population, means variance of the values existing in the population, the specific values, variance of that, and sigma square by n means variance divided by sample size. So, as n increases, as sample size increases, sigma square by n decreases, and square root of sigma square by n is called standard error, that also decreases. Standard error shows to what extent values obtained from sample data differ from sample to sample. This is a general rule which applies to all statistics based on sample data, including this m or m dash. So, as such, by just looking at m or m dash, you cannot say whether this value is so low that you can tolerate it and say that the theoretical distribution fits, or that this value is so high that you cannot tolerate the difference and theoretical distribution does not fit the empirical data. You have to keep in mind sample size. So, tables of m or m dash are also shown according to size of sample. This table shows that for a given level of significance 0.20, 0.15, 0.10, 0.05, 0.01. I will explain these 0.20, 0.15, what does level of significance mean while talking about hypothesis testing. These are the probabilities of rejecting null hypothesis even in those situations in which null hypothesis is correct. You see, you are dealing with null hypothesis. Null hypothesis may be correct, null hypothesis may be wrong, and your decision may be that null hypothesis is rejected or null hypothesis is not rejected. But null hypothesis may actually be correct or not correct. So, accordingly there are 4 situations when null hypothesis is accepted, but it is wrong, when null hypothesis is accepted when it is correct, when null hypothesis is rejected when it should be rejected, when null hypothesis is rejected when it should not be rejected. So, there are various types of errors and we will talk about type 1, type 2 errors later. This level of significance alpha is the probability of the error that you are rejecting null hypothesis when it is true, means theoretical distribution fits the data, but you are rejecting and for these values for sample size 3, 4, 5, I said that sample size is important in determining with what value of m you will compare your calculated value. So, for example, if you have a sample size of 10 and your level of significance is 0.05, sample size is 10, level of significance is 0.5. So, corresponding to 10 and 0.5 the value is 0.410. If your calculated value of m is less than 0.410, then you do not reject the null hypothesis that theoretical distribution fits the data. But if your calculated value of m or m dash is more than 0.410 and sample size is 10, then you have to reject the null hypothesis. Then you say that the distribution which I fitted actually should not be fitted to empirical data. If your sample size is 50 and you choose the same level of significance 0.05, then you are comparing your calculated value of m with 0.19. This 0.19 is less than half of this value 0.410 at sample size of 10 with which we are comparing earlier. So, this is because sample size is important. For larger samples we will expect less fluctuations, for smaller samples we expect more fluctuations. So, smaller samples the difference that can be tolerated due to sampling fluctuations will also be higher. For samples of size above 50, a general formula is given for different levels of significance, and for 0.05 it is 1.36 divided by root n, n is the sample size, and you see as level of significance declines from 0.20 to 0.01, this value over 50 increases. So, that means for as sample size is more and level of significance is declining, the threshold value of m is increasing. When means up to a higher value of m, you can tolerate the difference between actual distribution and theoretical distribution. So, for fitting a model, in this lecture we compare theoretical distributions with empirical distributions. Sometimes we are dealing with models, and models can be simple, models can be complex. So, we will discuss how to test goodness of a model in 2 lectures on regression analysis. Lectures on regression analysis will be indicative of how to fit a model and how to test whether a particular type of model fits the empirical data or not. In any case, it aims at estimating the unknowns of the models, same idea as in testing goodness of fit of theoretical distributions, and then we go for goodness of fit test, chi-square or SK test. Then in the first lecture I said that the aim of social sciences and that includes management sciences is to go for structural equation model which includes measures or empirical value, measures or concepts, concepts which are directly measured, and theoretical constructs and their interrelationships, and there are ways, chi-square is one, there are ways of comparing theoretical complex relationships or models with empirical relationships. Many of these measures are based on chi-square, and chi-square as I have defined is nothing but sum of squares of observed frequencies and theoretical frequencies divided by expected frequencies. Now, this takes us to some other issues also, in what situations chi-square will fit. So, there will be one lecture on chi-square. For example, chi-square should not be used when any theoretical frequency is less than 5, and some people say 1 depending on sample size. Also, chi-square depends on degrees of freedom, and there are other limitations, we will talk about them. But in structural equation model, which is the most complex form of model, you can compare theoretical model with empirical model by calculating chi-square for something like variance covariance matrix. Thank you.